agitation of the ratchet and pawl mechanism itself. Just as the paddle wheel is bombarded by randomly moving fluid molecules, so too is the pawl. This incessant buffeting causes the pawl to jiggle and lift intermittently, allowing the ratchet to slip backward against its intended direction of motion. Furthermore, the random vibrations can cause the pawl to bounce over the teeth, again permitting backward rotation. Feynman's quantitative treatment demonstrated that at thermal equilibrium, the average rate of forward rotation due to the Brownian motion of the paddle wheel is precisely balanced by the average rate of backward slippage caused by the Brownian motion of the pawl. Over time, there is no net rotation of the ratchet, and therefore, no sustained extraction of useful work. The apparent asymmetry introduced by the ratchet and pawl is negated by the inherent randomness that permeates the entire system at a uniform temperature. The device, therefore, does not constitute a perpetual motion machine of the second kind. The significance of the Brownian ratchet thought experiment extends beyond debunking a seemingly plausible perpetual motion device. It serves as a powerful illustration of the fundamental role of thermal fluctuations at the microscopic level. It underscores the fact that, at thermal equilibrium, all components of a system are subject to the same degree of random motion, and any attempt to create directed motion from this randomness alone is inherently futile. The second law of thermodynamics, which dictates the increase of entropy in an isolated system, finds its manifestation in the inability to extract order, directed motion, from complete disorder, uniform thermal agitation, without an external energy input or a temperature gradient. Interestingly, while the simple Brownian ratchet operating at a single temperature fails to produce directed motion, the underlying principles have informed our understanding of biological molecular motors. These remarkable nanomachines within living cells, such as kinesin and myosin, operate in environments characterized by significant thermal noise. However, they achieve directed movement by utilizing energy derived from chemical reactions, like the hydrolysis of ATP, and by interacting with asymmetric potentials along their tracks. These biological systems are not at thermal equilibrium. They actively consume energy to maintain their directed motion, thus adhering to the laws of thermodynamics. In conclusion, the Brownian ratchet stands as a compelling example of a seemingly paradoxical system that ultimately reinforces the fundamental principles of thermodynamics. While its initial conception suggested the possibility of extracting work from the random energy of a system at a single temperature, Feynman's rigorous analysis revealed the crucial role of thermal fluctuations in all components of the device, negating any net-directed motion. The thought experiment serves as a potent reminder of the pervasive influence of entropy, and the impossibility of perpetual motion without violating the established laws of physics. It also provides a valuable framework for understanding the challenges and strategies employed by biological systems to achieve directed movement in the face of inherent thermal noise, albeit through the input of energy and the maintenance of non-equilibrium conditions.